It's me again, Sir Ramon. We're going to yeet our projectile motion away and we're going to move on to our next topic, which is momentum and impulse. These are words that you may or may not have heard in your lives so far, but these are related to physics and how objects are in motion. All right, so again, it's how mass relates to motion. So if you looked at your kinematic equations, there's lots of quantities, lots of variables there, but the one that we don't see is mass. Wala bang mass ang mga projectiles natin? Is it the case that just because you throw something, suddenly it doesn't have any mass anymore? That's not the case. Actually, our kinematic equations are going to ignore mass, but in this case, with momentum and impulse, mass is important. Okay? So mass is still related to motion. So imagine this, if you have an object with the same speed, again, just going along at the same speed, but it has different mass, okay? It can have different, okay? It has different impact when it starts to hit you. Alright, so if you have something like this cute little heart eraser thing, if it's moving at a certain constant speed and then it hits you, okay. Okay? But if you have something like a huge whiteboard and it moves at the same speed, then you get hit. Okay, it hurts a bit more. All right. So again, mass has something to do with the impact of a certain object. So that's where momentum comes in. Momentum is a measure of mass in motion. When you have an object, it has mass. It has a certain amount of matter, a certain amount of stuff. And the more stuff there is in it, the greater the impact, the more oomph an object is packing when it is moving. Okay? So that's what we mean when we say momentum. It's object, it's mass in motion. So if we try to put that into a mathematical equation, we have the equation P, or momentum, is equal to mass times the change in velocity. So we write that as delta V. So again, you can see here your delta symbol, that's the Greek letter delta. That just means change in velocity. When we say change, we have a final velocity and an initial velocity. All right? So once again, you have a final velocity, and an initial velocity. When we say final velocity, this VF, we're looking at the velocity that comes after speeding up or slowing down. When we say VO or V initial, the initial velocity, this is the velocity that your object starts at. So we have number two over here, and velocity number 1 over here. All right? So when you get the difference between them, you get what is essentially your delta V, or your change in velocity. So if you measure how much your velocity is changing and you multiply it by the amount of mass, you get momentum. Now you can see you have these little arrows here, an arrow above the P and an arrow above the V. These mean that they are actually vector quantities. Again, when we say vector, it means that they have direction. Again, my direction sila. They're not just magnitude. It also says how, in what direction they are pointing to. Whether it's up, down, left, right, 30 degrees, 69 degrees. All of those different ways of expressing direction can apply to momentum and velocity. So everything we've been talking about with vector resolution. Again, vector resolution with your cosine theta and your sine theta. You're still gonna meet those when we discuss momentum and impulse. But going back, focusing on momentum, we have sample problem number 1. So here, we got some familiar names. Rainiel is about to be violently tackled. His only choice is whether he'll be tackled by Valerie or by David. If either of them will tackle him head on at 4.5 meters per second, what is the difference in their momentum? Who is gonna pack less impact? All right, so again, when we solve these problems, it's best if we try to look for the given first. All right, so first we have to extract the given from the problem, and it's easiest to extract the given from the problem if we draw the problem first. All right, so let's have a little drawing here. Let's have Rainiel. I'm gonna draw him with glasses. So Rainiel Uwu is over here. So we have Rainiel over there. All right, let's label him R for Rainiel. And then we have Valerie. I can't draw, so this is not gonna be very accurate. Forgive me, Valerie. We have Valerie symbolized by V, and then David, Mr. David, big boy. All right. Of course, we're gonna symbolize him with the first letter of his name. Of course, the D. All right. So we have a choice between David or Valerie, and in this case, we have numbers in our given. We have Valerie, who has 45 kilograms to her name, and David, who has 60 kilograms to his name. All right. So again, we have the mass of Valerie and the mass of David. So when we take note of our given, we have to take note that the mass of David is 60 kilograms and the mass of Valerie is 45 kilograms. All right, so we take those down. And we also have here the number 4.5 meters per second. Again, when we say meter per second, we have meters, which is for distance. We have meters over here. And we have time in the form of seconds. So distance over time is a unit for velocity. So we have our velocity, which is equal to 4.5 meters per second. All right, so this is our given for this sample problem. But sir, you said that there's a change in velocity. All right, there's a final velocity and an initial velocity, but there's only one velocity here. All right, so once again, we have what we call our hidden givens. When we have just one velocity given, that usually means that the hidden given is that the initial velocity is from rest or from zero. All right, so hidden given, you have initial velocity at 0 meters per second. All right, let's just emphasize that by having that on our board. All right, if we get our given, we have this as our given, and if we get our asked for, again, if we go back to the problem, we're asking for what the difference in their momentum is. And in order to get the difference in their momentum, of course, we'll have to solve for momentum. So our asked for is the difference between the momentum of Valerie and the momentum of David. And our formula is just the classic formula for our momentum. Our P is equal to M times V. All right. So if we plug in the values, we have the momentum of Valerie. Again, if we get the momentum of Valerie, we have her mass, 45 kilograms. Multiply that by 4.5, we get 202.5 kilogram meter per second. So please take note of our units. Our units are basically just this unit, the unit for mass, and this unit, the unit for velocity, put together. Again, if you just put them together, that's our unit for momentum. So even if I give you different units, your units for your momentum will just be the unit for mass and for velocity put together as one unit. All right? Now, if we look at David's momentum, we have 60 times 4.5. That gives us 270 kilogram meter per second. Now, what we were being asked for is the difference. Again, the difference between the momentum of Valerie and David. So we have to subtract the momentum of Valerie and David, and that gives us our answer 68. All right, so our final answer is that David has 68 kilogram meters per second more momentum than Valerie. And conversely, that means that he'll probably crush Rainier when he gets tackled. All right, so moving on. Again, our topic is momentum and impulse. So, how can we change the momentum of an object? If momentum is the mass in motion, how do we change that mass in motion? Again, when we change the motion of an object, we need to exert force. And in order to cause force, in order to change momentum, you have to change velocity. Of course, we can also change mass. However, let's put that away for a while because it's kind of awkward to be changing the mass of an object. Okay, so again, we usually just change the velocity of an object. So either you speed it up, you slow it down, or you change its direction. Once again, don't forget that if you change the direction of motion, it is still a change in velocity. It is still a change in momentum. Why? Because direction is part of being a vector quantity. Again, if you're a vector, you have magnitude and direction. So if you change the direction, you are changing that vector quantity. All right, so even if you're just turning left or right, that's still a change in momentum and a change in velocity. And changing velocity requires force. And that force is equal to mass times acceleration according to the second law of Newton. And if we substitute force is equal to mass times acceleration into our momentum formula, we actually get F delta t. Again, this is just mathematical manipulation. You can see that if you have F equals m times a, again, if you have F is equal to m times a, you can actually substitute your delta V as A delta T. Okay? But the basic thing that we need here, the most important thing we need here is F delta T, or FUT. And that is actually the definition for impulse. Impulse is an amount of force exerted on an object over time. So if you have object here, okay, our little heart eraser, if I exert force on it over a certain amount of time, I'm actually exerting impulse on it. And impulse can change momentum. So once again, your impulse is force times the change in time, or force times time. It's a force exerted over time. All right? And for the same amount of impulse, you actually have this relationship. If you have the same, if you need to give the same amount of impulse, you can do it over more time, so that you have to give less force. Again, I can change the momentum of this object by exerting force on it, either force that is very strong, again, more force over less time. So again, if it's moving and I slap it and it stops, so that's less contact time, less time, but it requires more force. You have to suddenly stop it. But if we give more time, to the object, again, more time. So again, if your object is in motion and you just nudge it with force over time, eventually it'll come to a stop. It'll require more time, but you have to give just less force. Again, if you have the same amount of impulse, you have the relationship of more time, less force, and less time, more force. Okay, they are what we call inversely proportional. All right. So also take note that impulse is also, typo there, a vector quantity. So also impulse, it has direction as well. So your impulse can be opposite to the direction of your object, in the same direction of your object, or in a completely different direction as your object. Okay? So your impulse can change the direction of your object. If you have momentum going one way and impulse going the other way, again, if they're opposite, you expect your object to slow down. But if you have momentum going one way and your force going the same way, then you expect your object to speed up. All right? So again, direction is very important for your momentum and impulse. So we go to sample problem number 2 to make sure that we understand impulse. So again, another familiar name here. We have Miss Grace, who is about to deliver a hand chop to your neck. And your neck will have to exert 500 Newton seconds of impulse in order to stop her hand. Okay? So what the question is, how much force will you experience if her hand chop lasts for 0.5 seconds, or if your hand chop exerts the force over 1 second? Okay, so again, we take down our given. So our given are specifically those that have been highlighted. So we have your impulse, which is equal to 500 Newton seconds. So let's write that down. And take note that we have an overbar on the second zero. Again, that overbar on the second zero means that it is significant. That particular zero is significant. All right, so that will come in that comes in as an important concept when we get to our final answer. Okay, and our other given is that her hand chop could last either 0.5 seconds or 1 second. Again, we have two times. Let's say we have a time for a quick chop and a time for a slow chop. So we have 0.5 seconds and 1.0 seconds. So this is our given. This is really all that's given. So again, we can take down the time it takes for the chop to happen and the impulse required to stop the hand chop. And since we are being asked for the force that you're experiencing, we have to manipulate our formula. Okay, so we can't just use the standard impulse formula. So again, we're being asked for the force of the quick chop and the force of the slow chop. And our formula, impulse is equal to force times delta t, we can rearrange it into force is equal to impulse over delta t. How did we get that, sir? Why is math so complicated? All right, so once again, if we start with J fat, J is equal to F delta T, we just isolate our F by dividing both sides by delta T. Again, if we divide both sides by delta T, as you can see here in the video feed, we get a cancel delta T and we get F is equal to J delta T, which is precisely our modified equation listed down in the formula. So if we solve this, we get your force of the quick chop is 500 Newton seconds, that's the impulse, divided by the change in time. Again, from the start to the stop of the chop, it's 0.5 seconds long. So if we divide that, we get 1,000 newtons of force. Whereas the slow chop, we have 500 Newton seconds divided by 1, which gives us 500 newtons. So as you can see here, the slow chop will exert less force than the quick chop, okay? Because the quick chop needs to be stopped even with the same amount of impulse. It needs more force for less time. Once again, if you have the same amount of impulse, you need more force if you're exerting it over less time. So our final answer is that Miss Grace will do 500 newtons of force over 1 second or 1,000 newtons of force over 0.5 seconds. So, kung leleegan ka, okay, you make sure that you spread out that force over time, alright? Save your neck. Since we can derive the formula for impulse from momentum, we can actually relate the two concepts together. Okay? And that gives us our impulse momentum theory. If you have impulse, you have momentum, you put them together, and we get this relationship. Your impulse is actually equal to the formula for momentum. Alright? So once again, they are actually equal to each other. Your impulse is equal to the change in momentum. Okay? Because impulse changes momentum. Alright? Again, you need the same amount of impulse to change the same amount of momentum. You can equate them. So again, you can use those two formulas and put an equal sign between them. What does that mean? We'll see in our sample problem number 3. Okay? We have 25 kilogram Mario driving in a 75 kilogram go-kart at a constant speed. Now, Princess Peach told him to come over. Her parents ain't home. So he stepped on the gas pedal for 5 seconds and sped up to 30 meters per second. Now, if the go-kart engine exerts 150 newtons of force, how fast was Mario going before he stepped on the gas? So, this is a bit of a complicated problem, and that's why we're going to do it together. So again, first things first, we need to get the given. So we have the numbers, 25 kilograms, 75 kilograms, 5 seconds, 30 meters per second, 150 newtons of force. What else is given? We also have this constant speed. Alright, so again, we highlighted the given in the problem. Okay, every time you read a problem, you need to extract all the information that you can get from it. So let's write these down. So the mass of Mario is 25 kilograms. The mass of his go-kart is 75 kilograms. We also have the constant speed. Now it says here that he was driving at a constant speed and then he sped up. So when we see this term, again, was driving or was traveling or was moving at this speed and then it changed, that means that the one that was mentioned before is the initial velocity, the starting velocity. So we list down that the initial velocity is constant. So as you can see here, We have our mass of Mario, mass of the cart, constant velocity. We still have our time, which is equal to 5.0 seconds. We have our final velocity, which is 30 meters per second, and we have our force, 150 newtons. So as you can see, golly wow, that's a lot of given. All right, so again, when it comes to momentum impulse problems, it's very important to be able to comprehend your questions and get all the given that's in the problem. And as you can see with the constant speed over here, not all the given will be in number form. All right, you need to read and understand your problem. So if we list down all the given, we get all this given here. And we have our asked for, which is the initial velocity. Again, we're wondering how fast Mario was going during his constant speed phase before he knew that Princess Peach was calling on him. And in order to get that, we need to use our momentum impulse formula. Again, we have here your F delta T, which is your impulse, your m delta v, which is your momentum, and your m delta v can also be written as m times final minus initial velocity. All right, so all three of those are the same. They mean the same thing. And the reason why we need that is because we're solving for this, your initial velocity. But our given only has our force, our time, our mass, and our final velocity. Again, we have everything that we need except for initial velocity. All right, because that's what we're solving for. Okay, so if we put all of the given into your solution, your force will be 150 newtons. Your time is 5 seconds. Your mass is, again, be very careful with your given, the mass of the cart plus the mass of the Mario. So 75 plus 25 kilograms. You multiply that by the final velocity minus the initial velocity. All right, so again, in this part of the problem, the first line of the solution, we are just substituting the given. We're just putting the given in the formula. Now, if we start solving the problem, we get 750 is equal to 100 times 30 minus VO. So again, we get to this part. Again, all we did was multiply 150 times 5. Okay? And we simplified 75 plus 25. Okay? Now, if we keep solving that, we get 750 is equal to 3,000 minus 100 initial velocity. Again, we just distributed your 100, 100 times 30, 100 times initial velocity. And finally, we isolate your initial velocity to get 22.5. So Mario was traveling at 22.5 meters per second before he started speeding up. But again, take note of your significant figures. If we look at your given, we have two significant figures for 150 newtons. Again, your 1 and your 5 are significant, but 0 is not. We have 2 here, 2 there, 2 there, and 2 there. So we should actually round this off to 23 meters per second, and that gives us our final velocity, our final answer, 23 meters per second. That was his initial velocity before he started speeding up. All right. So if you have any questions about momentum, about impulse, about momentum impulse theory, or about how to avoid getting your neck chopped, okay, don't hesitate to PM me. All right. I'm always there to help guide you guys, especially during your sample problems and your quizzes. So for your assignment, you have to do all of the sample problems listed here. Try to do them on your own, but you are free to refer to the sample problem solutions. Again, I don't expect you guys to get this wrong because you get the answers already. I just need you guys to practice so that when we have our exercises and when we have our quizzes, you guys are ready for the problem solving. All right? So once again, this has been Sir Ramon. I'll see you guys next time.